Okay, we're plotting solutions to a differential equation that look like this. So let me rewrite that down here. By the way, we also talked about what it meant for each of those pieces. So we're thinking about solutions of the form c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t v2. And so once we've solved the differential equation, the only thing that would be unknown here are the c1 and the c2, right, depending on your initial condition. Good, so we're going to try to look at solutions over all possible c1 and c2. And so again, our case 1 is going to be two real distinct lambda 1, lambda 2 with corresponding vectors v1 and v2. And so case 1a, we can say, is let's say lambda 1 is negative and lambda 2 is positive. You could do it the other way too, but that's just one way to look at it. Okay, and so just for specificity, let's say that lambda 1 is minus 2 and lambda 2 is positive 2. Okay, and then so now we're taking a look at solutions of the form c1 e to the minus 2t v1 plus c2 e to the positive 2t v2, just so it makes more sense to see what's going on. And now let's go ahead and plot our v1 and v2. So v1 is up here somewhere and v2 is down here somewhere. Okay, so now let's pretend that c1 is equal to 0, right? And so we're just looking then at c2 e to the 2t v2. Now what's that going to look like for different values of c2? And then what happens over time? So over time, well, for any c2, that's going to be along this vector somewhere, right? It'll start somewhere along the vector, and then if c2 is negative, it would start down here. Oops, that's along the same line, but it would just start somewhere there or there. Okay, and then as time goes by, what happens? The vector will be heading away from the origin, right? Good. Now let's reverse the process. Suppose that c2 is equal to 0, and let's take a look at c1 e to the minus 2t times v1 for different values of c1. So v1's over here. I'm going to use that arrowhead. So for different values of c1, right, this is just a constant multiple of v1, and so it's going to start somewhere along the line here, again depending on what the value of c1 is. But then what happens over time is, because this is negative, right, these are all going to the origin, and so these are all heading towards the origin along the vector v1. Good. And so that takes care of these two special cases, and now we want to look at what happens in the general case. Right, so looking at c1 and c2, right, this term is going to 0, but this term is blowing up. And so therefore, all your other solutions are going to be blowing up in the direction of v2. Blowing up in the direction of v2. So if I started over here somewhere, my vector might bend a little bit, but it's going to be going out to infinity along the vector v2, because this part of the solution is going to 0. Okay, and so we might have curves like this. Okay, and then the outside curves might go like that. Similarly down here, this is just the flip of that. So these are all heading towards infinity along v2. Right, and now we have to decide what happens in these regions here. So what happens in this region and in this region? Well, still the same thing's going to happen, right? We're going to be going to infinity along v2. So what's going to happen is they're going to bend a little bit and then head away. Bend and head away, bend and head away. And these are bending out this way. Okay? And so the origin in this case is called a saddle. Origin is a saddle. And in the case of a saddle, well, number one is that you have eigenvalues that are different in sign, and all solutions go away except for one particular set of solutions, and that particular set of solutions is along the eigenvector, right, that corresponds to this solution. Okay, all other solutions blow up to either positive or negative infinity. Very good. So that is case 1a, and the origin is a saddle when lambda 1 and lambda 2 are different in sign. Good. Now the next case is similar. I'm going to have two distinct real eigenvalues, case 1b, but in this case I'm going to suppose that they're both negative. Right? And so I'm going to have x of t, and just for specificity, let's say that we have c1 e to the minus 1/2 t v1 plus c2 e to the minus 2t v2. Okay, just to have specific numbers to work with. Okay, so then we look at our vectors again. We'll use the same vector v1 and v2. And now what's going to happen if you start along each of these vectors, and again, we could start off with the case where c1 equals 0, right? Then c2 would be c2 e to the minus 2t v2. And so all of these solutions we can see would be heading towards the origin instead of away. And then similarly, if c2 is 0, we would have c1 e to the minus 1/2 t v1. And all of those solutions are starting or going towards the origin as well. So in this case, all solutions are heading towards the origin. Good. What happens to all the other solutions? Well, if we look at this combination of vectors here and think about t going to infinity, or t getting bigger and bigger, which of these terms, the first or the second, goes to 0 faster than the other? Well, the one with the bigger eigenvalue, like negative 2, goes to 0 faster, right? Which means that if this part of the vector is 0, then the solution is going to be guided towards v1. Okay, so that means we're going to be moving in towards this vector. And so when the solutions are coming into the origin, they all are, they're going to be coming in tangent to v1. So what does that mean? It'll look something like this, right? Except the direction will be going that way. Solutions will be going that way. Okay, and maybe I'll take a different color. And so which one was v1 again? This was v1 right here, right? So solutions are going to be tangent to that guy, tangent to that guy, moving towards the origin. This was tangent, right? Tangent. Good. And so what happens to these other vectors? Well, if I start somewhere out here somewhere, what's going to happen is the vector will still come in tangent, but it might take a little bit to get in there. Okay, so these will still come in tangent to this vector, right? Okay, similarly over here, these guys will come in around this way. It'll still be a little bit tangent. Okay, and so again, that was the vector along which the eigenvalue was the smaller of the two in negative terms. Okay, and so the origin in this case, is a sink. And a sink is stable, asymptotically stable. Okay. And finally, case 1c, I guess we're on, right? Case 1c. If lambda 1 is bigger than lambda 2 is, well, if they're both bigger than 0, I guess is what I was saying before. Then what happens? Well, actually, it's the same picture as the sink. So let me draw that picture. That was v1 here and v2 there. So I'll go ahead and draw the V1 and V2 in here. And we said that solutions to the sink were coming in tangent to V1, tangent to V1, and all the other solutions are coming in tangent to V1 like that, right? Now what happens to if the eigenvalues are opposite in sign is that you just reverse all the arrows that you had before. Just reverse all the arrows. Good. And so this is called, the origin is a source. Okay, so a source is where both of your eigenvalues are positive. And the way to draw a source is to first draw it as if it were a sink. Think about what would happen, if I had lambda equals 1/2 and lambda 1 and lambda 2 equals 2. And so negating those would give me, the previous case. So I would go ahead and draw this picture without the arrows, and then the arrowheads would just come in reversed. Okay, and that would give me the source. So it's a lot easier to draw a sink than it is a source. Good. All right. And so that takes care of case 1. In the next video, we're going to talk about the complex situation, the situation where we have complex eigenvalues, and then we'll try to do a bit of a wrap-up.